How does a robot make sense of the world around it, just like we do when we read a captivating story? Think of a fictional book as a huge collection of numbers for a robot, like a spreadsheet full of complex calculations. How does the robot turn these numbers into a meaningful picture of the world and use it to make smart decisions? In this video, we will explore the fascinating field of artificial intelligence and look at a student's homework project. We will reveal the hidden mechanisms behind building a system that can understand the core of a story and give it a unique artistic flair. As always, I have prepared Colab notebooks, like detailed maps, that contain all the code we will see in action today. I encourage you to dive into this code, like a mechanic adjusting the parts of a sophisticated machine. As we delve into the realm of artificial intelligence, we must pose a crucial question. How can a robot truly comprehend the depths of human literature? To unravel this enigma, we embark on a literary adventure, selecting a book as our guide. Which literary masterpiece should we select as our beacon in this quest? I have submitted this question to the internet. What book is free from copyright, which has been made into many movies and which is included in many famous book lists? A book which is loved by both adults and teenagers, a book which is also known in China, Russia, and other countries. The resounding reply from the internet echoes through the corridors of literary history. The Hound of the Baskervilles, by the venerable Arthur Conan Doyle. Indeed, this work stands as one of the most celebrated detective chronicles, and now we shall witness the computer's attempt to dissect it, unveiling its comprehension with the grace of Sherlock Holmes himself. However, before we can test the computer's understanding, we must first ask ourselves how we can prove that we understand what we have read. One way to demonstrate comprehension is to create something new based on the original work, such as a movie, a play, a game, or a cartoon. Let's take a specific excerpt from the book. I'll read it, and you see how various directors have depicted this scene in their works. Mr. Sherlock Holmes was seated at the breakfast table. I stood upon the hearthrug and picked up the stick which our visitor had left behind him the night before. "Well, Watson, what do you make of it?" Holmes was sitting with his back to me, and I had given him no sign of my occupation. "How did you know what I was doing?" "I have at least a well-polished, silver-plated coffee pot in front of me," said Holmes. This scene is like a puzzle, where you must identify the essential objects such as Sherlock Holmes, Watson, the cane, the polished silver coffee pot, and place them in a logical-looking scene. It's like a game of chess, where you have to think ahead, or as the famous quote goes, "Elementary, my dear Watson." I trust that you grasp our endeavor in decoding the enigma of artificial intelligence, illuminating its prowess in comprehending text. Our aim is to sift through the tapestry of words and distinguish from the text the objects that we would like to place on the stage of the work being created, much like a director curating a theatrical performance. In our case, this stage takes the form of a canvas, awaiting the strokes of a generated image. Before we delve into the realm of Python code, let's explore the world of AI systems that can generate images from text. Welcome to the AI Systems Art Gallery. Our initial contender is the DALL-E. Alas, the outcome before us falls short of our expectations, shrouded in perplexity. The enigma persists as to why this system missed the essence of the scene, like an actor stumbling over lines in a pivotal moment. Simplified.com takes the center stage, offering a more refined rendition. We can discern the presence of some objects, yet the choreography of their arrangement leaves room for improvement, like a painter striving for a more harmonious composition. Now, Stability AI steps into the limelight, delivering a remarkable performance that tantalizes the senses. Nevertheless, it stumbles in recognizing key elements, such as Watson and the stick, akin to a gifted actor momentarily forgetting their cues. In a twist of fate, Bing Chat surprises us with its proficiency in conjuring captivating images. It's intriguing to note that this system draws inspiration from DALL-E, despite the latter's earlier misstep in our test. As we can see, some artificial intelligence programs can accurately represent the text scene, while others cannot. However, it's essential to acknowledge that these are proprietary software systems, often demanding a payment if you want to get a generated photo of better quality or to integrate image generation into your own systems through API. Moreover, their scope remains limited, focusing on concise text fragments, where they often isolate a single object, but do not provide a generated scene containing all the objects mentioned in the text. Our artistic stage is a canvas yet to be filled with the masterpiece of the future. Today, our mission is to embark on a creative journey, wielding the Python programming language as our paintbrush, and breathe life into the pages of any book through the art of artificial intelligence. This is not an easy homework, so just like an artist who breaks down a complex canvas into smaller Google Colab notebooks, picture it as 4 interlinked Colab notebooks, each carrying the set of knowledge and passing it to the next stage. In our first task, we will load the book into the computer memory, and we will create a word table with the spaCy library by adding all the information provided by the spaCy library. Additionally, we will mark chapter and paragraph for each word in this table. The second notebook shows how to find semantic type for each word using the NLTK library and the WordNet dictionary. From such information, we will be able to select words that denote real-world objects and which we can put in the scene of our image. Such a complex text as a novel is characterized by the fact that in different parts of the novel, the same object is presented using different words and phrases. In computational linguistics, this is the so-called coreference task, and for this task, we will create a separate Colab notebook where you will find an example of how to integrate the Stanford CoreNLP Java technology system into the Google Colab environment, and using it solve coreference task. Our final and perhaps most exhilarating task involves generating book illustrations from carefully selected words and phrases, utilizing the open-source image generation library, Stable Diffusion. You can find links to the solutions to all these tasks below this video. I will finish this video by explaining the main ideas of each notebook. As we embark on our journey through the realms of natural language processing, think of our first Google Colab notebook as a portal to a literary universe. So we begin by opening the first Google Colab notebook. Our objective is to store the content of a novel in the computer memory as a separate table of words, where we have grammar and some semantic information about each word. Next, we launch Run All. Our notebook will be processed in a couple of minutes, and the Hound of Baskerville's novel word table will be ready for exploration with interactive Pig Walker tool. Now let's delve deeper into the magic we've conjured. The first step is to download the novel from the Gutenberg project and put the lines of the book into a data frame table. For this, we need a variable that stores the URL link to the book, as well as a variable that describes a regular expression that allows us to determine when the book chapter changes. With these variables at our disposal, we invoke a function designed to fetch the contents of the book and return them to us in the form of a data frame table. Those versed in the art of natural language analysis recognize that data preparation stands as one of the most formidable challenges in this process. One of the primary challenges within this phase lies in the removal of extraneous information. It is discerned that the getLines function not only retrieves the desired text, but also includes metadata from the Gutenberg project. Consequently, we introduce a new function that expunges these superfluous rows from our data frame, leaving only the essential content intact. In many natural language processing projects, the focus typically centers on individual sentences or short text fragments. However, to grasp the narrative contained within the novel, the structure of chapters and paragraphs is of paramount significance. Accordingly, we introduce another function to merge lines into paragraphs, thus generating a fresh data frame where each line corresponds to one paragraph within the book. Dialogue constitutes a substantial portion of the text within a novel. Identifying the locations of dialogue within the narrative offers insights into the characters present in a given scene. To conclude our data preparation phase, we invoke a function that discerns whether a paragraph contains dialogue or not. Finally, we arrive at the point where we have successfully transformed the book's text into a structured table, with each row representing a paragraph. This tabular format allows for further analysis using natural language processing libraries. Our initial encounter is with spaCy, a versatile library for natural language analysis. spaCy facilitates fundamental tasks such as part-of-speech analysis, enabling the identification of grammatical word forms such as nouns, verbs, or adjectives. Furthermore, spaCy equips us to recognize entities such as names of individuals, locations, and temporal references, a task known as named entity recognition. The process is straightforward. We provide a paragraph as input, and in return, we receive an annotated document, which can be processed programmatically to generate a word table enriched with relevant linguistic information. Our introductory Colab notebook concludes with an exploratory data analysis facilitated by the Pigwalker library. This tool provides an intuitive interface for data exploration. By simply inputting our word table, we gain access to a range of analytical features. Within this interface, we can chart the distribution of words in each paragraph by dragging the chapter column onto the x-axis and the row count column onto the y-axis, generating a graphical representation of the text's structure. Additionally, incorporating the is-speech column into the color field enables us to discern the prevalence of dialogue within various sections. Pigwalker serves as a valuable resource for initial data analysis, offering an immediate and comprehensive understanding of our dataset. In our exploration of natural language processing (NLP) tasks, the spaCy package proves to be a valuable tool for extracting information about words in a given text. However, its named entity extraction algorithms only provide entity types for a limited set of nouns. Consider the word table. spaCy recognizes it as a noun, but it doesn't discern its specific meaning, whether it represents a tangible object with mass and volume or an abstract entity like a data table. To delve into the deeper semantic meanings of words, we turn to the NLTK library and leverage its WordNet module. In my second Colab notebook, linked below this video, I walk you through an example illustrating how to achieve this. In a nutshell, NLTK and WordNet enable us to uncover the nuanced meanings of words. Take the sentence, "Mr. Sherlock Holmes was seated at the breakfast table," as an example. Applying the NLTK method LESK to the word table, we extract its semantic meaning. In this context, we discover that table refers to a physical object in the furniture class, possessing mass and suitable for placement on a stage. This process allows us to gather enriched information for all the words in our text and conveniently store it in Google Drive for further analysis. Explore the second Colab notebook for a hands-on demonstration of this methodology. In the third Colab notebook, there's a comprehensive example of Python code demonstrating the augmentation of our text with the use of Stanford CoreNLP, a prominent natural language library. This library becomes instrumental in resolving what's known as the coreference problem, where we aim to determine which words refer to the same object. For instance, consider these lines from our text. "I stood on the hearthrug and picked up the stick which our visitor had left behind." Well, Watson, what do you make of it? Through the coreference module, we uncover that I refers to the book's protagonist, Watson. It refers to the object, stick. Visitor points to the book's central character, James Mortimer. And our pertains to the duo of protagonists, Sherlock Holmes and Dr. Watson. For a deeper dive into the coreference task and insights into integrating the Stanford CoreNLP framework with NLTK and spaCy, the third Google Colab notebook offers a wealth of information and detailed algorithms. Our final task in this journey through NLP involves bringing the book to life visually, an endeavor detailed in the fourth Colab notebook. Pooling data gathered from various NLP libraries, we aim to craft descriptive phrases, encapsulating scenes, and then utilize the stable diffusion model to translate these phrases into scene images. Within the provided Colab notebook, a rudimentary algorithm serves as a starting point, focusing on extracting noun phrases from the narrative segments while excluding dialogue. These extracted phrases, depicting either the novel's protagonists or physical objects, are grouped for further processing within the Stable Diffusion image generation library. It's important to note that this algorithm doesn't incorporate details from Stanford CoreNLP, like coreferences or word dependencies, leaving room for enhancements leveraging this information. The journey culminates with the exploration of the Stable Diffusion library itself. I've shared 3 code snippets within the Colab notebook to demonstrate its capabilities. The first code snippet allows experimentation with various drawing styles. By providing a Python list featuring over 50 image drawing style names and combining them with descriptive phrases, for example, the detective watches from the top of the mountain, a flaming dog runs along the mountain. Different images are generated for each style description. Choose the style you like best, and then run a second code snippet that takes the phrases we formed, adds a style description to them, and generates an image. Lastly, the final code fragment illustrates how to merge these images into a single video file. I present this generated file to you, inviting further exploration and enhancements in novel analysis while striving to create more refined and evocative visual illustrations for the narrative.